Now, children, we are going to discuss the fourth question in the tune that I gave you. So let me to share that tune first. I mean the question. Uh, you see, we are going to discuss this question now. Ammonia reacts with water in the reversible reaction. Which are the Bronsted-Lowry bases? Right? Which are the Bronsted-Lowry bases? So that is what the question is. Fourth question: ammonia reaction with water in reversible reaction. Which are the Bronsted-Lowry bases? So now, when I concern the answer for that, see that ammonia reacts with water. Now we concern the reaction between ammonia and water. See this ammonia. Now, if I write the ammonia like this way, ammonia reacts with water and it makes what? Ammonia reacts with water in reversible reaction, which are Bronsted-Lowry bases. Which are Bronsted-Lowry bases? Now, when the ammonia reacts with water, ammonia has a lone pair. The lone pair can accept the proton donated by water. So water is the proton donor there. So the water is the acid and ammonia is the base. So now ammonia, the NH3, get H from this water and makes NH4 plus and makes NH4 plus, which is ammonium. And then plus what? OH minus. Now, why the NH4 plus becomes? Because NH3 gain H becomes NH4 plus and water lose H plus, so it becomes OH minus. In the reverse reaction, ammonium ion donate H plus to OH minus. In the reverse reaction, ammonium ion donate H plus to OH minus. So the OH minus is the base and NH4 plus is what? Acid. So they ask ammonia reacts with water in a reversible reaction. Which are the Bronsted-Lowry bases? See that ammonia is a base. Ammonia is a Bronsted-Lowry base. And the OH minus is the Bronsted-Lowry base. So the answer is what? The answer is ammonia and OH minus. These two act as a Bronsted-Lowry base. So the second one is the answer. Right, the second one is the answer. Now I go to my question number 5. Right, question number 5. Yes. Now we see that question number 5. It has three parts. Let me show the question first. Now in this one, they ask question number 5. They ask, suggest the most likely pH for each of the following solutions. They have given 5 moles per cubic decimeter hydrochloric acid, and the other one is 0 0.1. Please make it as 0 0.1 moles per cubic decimeter strontium hydroxide. The next one is a mixture of 20 centimeter cube of 1 moles per cubic decimeter nitric acid and 10 moles per cubic decimeter sodium hydroxide. Right. So, like that, a set of questions they ask. So we will see that the first question, suggests most likely pH for each of the following solutions: 5 moles per cubic decimeter hydrochloric acid. So we see how the answer is made for that. Uh, the first question: 5 moles per cubic decimeter hydrochloric acid. Right. So then now we concern this one. Hydrochloric acid. So we are talking about a hydrochloric acid, which is a strong acid. Hydrochloric acid fully ionized, I mean 100% ionized like this way. Hydrochloric acid 100% ionized like this way. So now what will happen if the concentration of HCl is 5 moles per cubic decimeter? Since HCl is a stronger acid, concentration of H plus also should be what? 5 moles per cubic decimeter. 5 moles per cubic decimeter. So that's easy. We know the H plus concentration directly. So we can assign the value for the pH equation. pH is equal minus log H plus concentration. So the pH is equal minus log 5 is the concentration of H plus. So the answer is, if you use the calculator and find the answer, if you use the calculator and find the answer, you will see the answer is minus 0.7. You will see the answer is minus 0.7. So that is how the answer is coming for that question. If you want to clarify something, please pause the video and then check it. Right. I got next one. 0 point, it is missing, so please write it as 0.1, please. It should be 0.1. 0.1 moles per cubic decimeter strontium hydroxide Kw is given, right? So we want to find the pH of this solution. See that we want to find the pH of the solution. This solution is strontium hydroxide solution. Uh, Concentration is, we consider it as 0.1 moles per cubic decimeter. That's the concentration. And Kw is given. Kw is, we know that is 1 into 10 to the power minus 14 is the Kw value. So they ask, what is the pH of this solution? What is the pH of this solution? Now see, this is very easy question. This is very easy question. So what will happen? Strontium hydroxide is the strong base, right? Strontium hydroxide is a strong base because it is below in the group 2 hydroxide. I told that in the earlier question also, right? Um, we discussed earlier question regarding the barium hydroxide. There, the barium hydroxide is a strong base. I told you. Similarly, strontium hydroxide also strong base. So it is fully ionized. So Sr2 plus NOH minus 2, 2OH minus. And the next thing, the concentration of barium hydroxide, strontium hydroxide is given. Concentration of strontium hydroxide is 0.1. So the hydroxide concentration is 0.1 into 2, right? 0.1 into 2. Now, then I know this one, Kw is equal H plus concentration into OH minus concentration. I know the Kw value is 1 into 10 to the power minus 14. Or else I can subject H plus. H plus concentration is equal what? Kw over OH minus concentration, right? So then the Kw is equal 1 into 10 to the power minus 14. OH minus concentration is 0.2. So then we got that H plus concentration is how much? 5 into 10 to the power minus 14. So now we can assign this value for the pH is equal minus log H plus equation. So the pH is equal minus log 5 into 10 to the power minus 14. So pH is equal to 13.6. We got the answer 13.6. If we use the calculator, the answer will be 13.6. Right. Now, this is how we come to this one. Similar question we did earlier also. Now, this one also quite similar. Right. Now I go to the next one. That is the C part of that. A mixture of 20 of 1 moles per cubic decimeter nitric acid and 10 centimeter cube of 1 moles per cubic decimeter sodium hydroxide. So there is a mixture. Uh, there are two items. One is nitric acid, and the other one is sodium hydroxide. The other one is sodium hydroxide. And then from the nitric acid, how much we take? 20 centimeter cubes we take. From the sodium hydroxide, how much we take? 10 centimeter cubes we take, right? And then these two are mixed together, and nitric acid concentration is 1 moles per cubic decimeter. I put it at 1 m. Sodium hydroxide concentration also 1 m. And these two mixed together. So the total volume is what? 30 centimeter cubes. 30 centimeter cube is the total volume. You need to remember that. The total volume is 30 centimeter cube. Right. The total, 1 minute, total volume is 30 centimeter cube. Now, then I will find nitric moles, HNO3 moles. How to find the nitric moles? N is equal CV. Nitric moles, N is equal CV. Concentration is 1. Volume is 20. To convert to decimeter, divide by 1000. So the answer is 0.02 moles, right? And then I can find sodium hydroxide moles. Sodium hydroxide moles, how much? That also N is equal CV. N is equal C. The concentration is 1. Volume is 10 divided by 1000. So it is 0.01 mole. So you know there are so nitric 0.02, sodium hydroxide 0.01. So nitric is more. Therefore, HNO3 moles remain when they react. HNO3 moles remain how much? HNO3 mole remaining 0.01 because this minus this, right? The 0.01 moles remaining in which volume? 0.01 mole is remaining in 30 centimeter cube. Convert to decimeter cube to find the concentration. So this is what the concentration we can find. If we have the calculator, you can find it now. Right, when we find the concentration, that is 0.01 divided by 30. So it is 0.333 something. So it is 0.333 something. So nitric is a strong acid. So H plus concentration is how much? 0.333 something. So you assign that for the pH equation. When you assign that for the pH equation, so then now you will get the answer as 0.48. pH will be 0.48. That part is easy. You apply that for the pH equation, right? So the next part, that is now we go to sixth question number 6. Now we go to sixth question number 6. In liquid ammonia, the following equilibrium is present: NH2 minus NH4 plus gives ammonia. Identify the Bronsted-Lowry base. identify the Bronsted Lowry base. Similar question we did earlier also. See that NH2 NH2 minus plus what? NH4 plus. It gives 2 ammonia. 2 ammonia here NH3 plus NH3, right? So now what will happen? Now what will happen? Here, this is the bronze fluoric acid, hedonate H plus. So this is acid and this NH2 is what? That is the base, right? And here ammonia and ammonia is there. One of that ammonia has to be act as a base. One of the ammonia has to be act as a acid. Any one of that is acid, right? The other one is what then? Base. So which are acting as a basis? NH2 minus and ammonia is acting as a basis. So the answer for the sixth question is C, right? So I go to question number 7 now, right? It is quite long question. So I will share that. We will read the question early before we go to the answer, right? So this is the question number 7. A solution of potassium manganate 7 was used to determine the concentration of iron 2 ions in solution by titration in the presence of excess dilute sulfuric, right? With the potassium manganate 7 in the burette, the end point of the reaction is when the solution in the conical flask turns colorless pink, green, and orange. The B part, insufficient acid is added, the titer value, you have to say something about the titer value. First, we will go to the question number 7a part. So when I concern this question, that is asking about the titration. That is asking about the titration. A solution of potassium manganate 7. Potassium manganate 7. A solution of potassium manganate 7 was used to determine the concentration of iron to iron in the solution by titrating in the presence of dilute sulfuric acid. When the potassium manganate 7 is in the burette, see that this is my burette. In the burette, what is there? In the burette, what is there? KMnO4. In the burette, what is there? KMnO4. Potassium manganate 7 is in the burette. And then, the potassium manganate 7 is in the burette. So KMnO4 is here. And what is here? Fe2 plus. Fe2 plus is in the class, right? With the potassium manganate 7 in the burette, the end point of the reaction is when the solution in the conical flask turns. At the end point, it turns to which color? At the end point, it turns which color? At the beginning, it is pale green or colorless. When all the Fe2 plus is finished, the next coming drop of KMnO4 will dominate the KMnO4's color in the titration flask. So the KMnO4's color is pink, so it will be pink. That is easy. The next part. If insufficient acid is added, the titer value is. So see that when we concern KMnO4 reaction, so what will happen? MnO4 minus should be converted to what? Mn2 plus. Mn2 plus. So to be balanced that, we add 5 electrons and 8 H plus. right? 8H plus. So what will happen? And it makes 4 moles of water, right? So in the other side, meanwhile, Fe2 plus becomes what? Fe3 plus an electron. So it happens like this way. This is what the reaction takes place there. This is what the reaction takes place there. Now you can understand in if insufficient acid is added, if the amount of acid is added less, so then what will happen if the amount of acid less, MnO4 minus reactant will be less. So then what will happen? The titer value. So Kmno for use is less. So the titer value will be reduces, right? And meanwhile, that Fe2 plus is not utilized. There's no agent coming to react with Fe2 plus. So Fe2 plus makes Fe3 plus. Fe3 plus is a brown precipitate. Then Fe3 plus makes high oxidation. It undergoes oxidation. If it makes FeOH twice, which is rust brown precipitate. So the titer reading will be low and then the precipitate will be high. The precipitate will be brown. So that is what the answer is. Now, the next point, the next question is the eighth question. The eighth question is about phenylamine, methylamine, and ammonia, like these things. This is regarding the basicity of that weak basis of the organic chemistry part. So then I didn't discuss the organic chemistry part yet, so I will skip that question because with you all in your class, I didn't discuss the organic chemistry. The ninth question, the dissociation constant of water increase with increased temperature. When the temperature increase, the water remains neutral, dissociate less, becomes acidic, becomes alkaline. So now when I concern, see this one, the dissociation constant of water. See that dissociation of water. What is dissociation of water? H2O is there with the presence of H2O only. That means pure water only there. When pure water only there, then one water molecule has to act as an acid, the other one has to act as a bronzatory base. So one of these donate H plus to this one and the other accept that. So ultimate result is H3O plus and what? OH minus. So this is endothermic process. It is endothermic process. Delta H because it's bond breaking. This bond is breaking, right? Right. So the next one, I mean, similarly, water becomes H plus and OH minus like thing happens, right? Now you can understand that is bond breaking. These two are similar, right? So the same thing is there. Bond breaking happens there. So it is endothermic process. This is endothermic process. The dissociation constant of water Kw. So if I write the expression for the Kw, early before the Kw, I can write the Kc. Kc is concentration of H3O plus, concentration of O minus, divided by concentration of water to the power 2. Right? Now think about this, that this one bring here. So we write that is Kw. Kw is equal what? H3O plus concentration and OH minus concentration. Right? Now, when the temperature increases, system also decrease the temperature. Therefore, the forward reaction promotes, right? Forward reaction promotes means more H3O plus and more OH minus produces. More H3O plus and more OH minus produces means this half becomes bigger. This half becomes smaller. So the Kw value will be bigger, right? Kw value will be bigger. Doesn't matter how bigger that is. Earlier, H3O plus, I mean earlier Kw, the Kw earlier 1 into 10 to the power minus 40. That means how much of H3O plus? 1 into 10 to the power minus 7. How much of OH minus? 1 into 10 to the power minus 7. It is early before I increase the temperature. When the temperature increases, Kw should be higher. It will be 1 into 10 to the power minus 12. So this also should be increased, 1 into 10 to the power minus 12. This also will be increases 1 into 10 to the power minus 6 and 1 into 10 to the power minus 6 like. Clear? So now see that Kw value increases. Yeah, Kw value increases, but H3O plus 1 into 10 to the power minus 6. OH minus also 1 into 10 to the power minus 6. So even though I increase the temperature, H3O plus and OH minus both increase in the same quantity. Finally, H3O plus and OH minus is same. So amount of acid and base is same. So the reaction is remain neutral. So for the ninth one, answer is pasta. For the ninth one, the answer is pasta. I think you understood that. Then I go to the next one, right? That is because very simple earlier one, when the reaction temperature increases, forward reaction promoter. So this one, how much produces? Same amount of OH minus also produces same amount of H plus and OH minus, means it is neutral. Right. So then I got the question number 10. The reaction between the concentrated sulfuric acid and pure ethanoic acid is given like this way: sulfuric acid and pure ethanoic. So I will write that equation first. Ethanoic acid is CH3COOH plus sulfuric is what? H2SO4, and it gives what? CH3COO H2 plus H2 plus and HSO4 minus HSO4 minus. Right, I guess you can see that now, right? HSO4 minus. That's the way it happens. Bronzochloric acid in the equilibrium are. Now see this one. This has only one hydrogen. There are two hydrogen. That means he accepts H. So he donates H. So this is the acid. Right. Okay. And in the reverse reaction, this one HSO4 minus, reverse way H2SO4. So this one accept H plus, right? So this is the acid. So what are the acids are? Uh, Sulfuric acid, and what are the acids are? The sulfuric acid and this thing CH3COOH2 plus. Right. So the next one, we go to question number 11. An aqueous solution of ethanol. We go to question number 11 now. Right. An aqueous solution of ethanoic acid is gradually diluted. Which of the following statement is incorrect? An aqueous solution of ethanoic is gradually diluted. Which of the following statement is incorrect? Right. Incorrect. They ask incorrect. Right. So see this one. Aqueous solution of ethanoic. We consider ethanoic solution. This is CH3COOH. This aqueous solution of ethanoic behaves in this manner. Behaves in this manner with water. It makes H3O plus and CH3COO minus. CH3COO minus. CH3, that now aqueous solution of ethanoic is gradually diluted. Which of the following statement is incorrect? Now this is the way it reacts. Right. When this solution is diluted, when I add water to this one, right. So see that pH decreases. pH decreases means H3O plus, pH decreases means H3O plus concentration increases. pH Decrease means low pH decrease means what? Acid. pH decrease means what? Acid. That means what? Means H3O plus concentration should be increased. When the water added H3O plus increases, no, it cannot happen. So this is the answer. Right. And the next, see the B, the value of Ka unchanged. That is correct. Ka is only changed with the temperature. We add water, but they didn't mention that temperature change. So Ka is a factor change only with the temperature. With the addition of water, they didn't mention temperature change. So no change in the Ka value, right? So actually the first one is the answer. Why? They says pH decrease. If pH decrease, low pH 0, 1, like low pH means good acid. pH decrease means acid. That means H3O plus concentration should be increases. But when we add water, H3O plus concentration surely decreases. Okay? So that is how it happens. Sometimes student must has doubt, oh, how it happens. When you add water, H2O concentration increases. So the forward reaction promoted, H3O plus concentration when we add water, H2O concentration increases, so the forward reaction promotes. Therefore, more H3O plus produces, so pH should be decreases. The first statement is correct. Sometimes student can argue. Remember that I have told you many times, water is large excess. Concentration of water is constant. Concentration of water is constant. How much you add water to the sea, never it get diluted. How much of water you added to that. Some places already water there. The other water concentration is not changed. The other concentrations change. Right. So then that is how uh, up to the 10th question. The next question onwards we come through the another video.